I'd like to welcome everyone to the 2014 SU Research Day and Innovation Showcase. I'm Clifton Griffin, Dean of Grad Studies and Research. First and foremost, thank all of you for being here. In particular, I'd like to thank our Provost, Dr. Allen, sitting back here for her support for this event and for research and scholarship overall. This day is about creating connections. Those connections are important, whether it's faculty member to faculty member right here on campus, or it's creating connections between our campus and the outside community. That's what we hope will be the takeaway message from your presentations today. As you can tell from the program, we have a wide array of topics. It's going to be fascinating. I can't wait. I've already had a little bit of a snippet of almost all of the presentations, and I can tell you, you will be wowed. Also awesome to see some of last year's presenters who are here supporting folks from this year. We certainly appreciate their participation and their being here. Our next presenter is Dr. Sophie Wang. She comes to us from the Department of Mathematics and Computer Science. She's going to talk about improving prediction and visualization of coastal inundation on the eastern shore of Maryland. Easy for her to say.
Thank you. Good evening, everyone. Thank you for coming to my talk. And I'm going to talk about improving prediction and visualization of coastal inundation on the eastern shore of Maryland. It's not that easy for me either. Now, this is a recent article from Washington Post. And this article talks about the flooding from storm surge would threaten DC infrastructure. And here is another interesting one. And this reminds me of what Jennifer was talking about, what journalists do. See, in this picture, you actually see the Jefferson Memorial is being flooded. And this article is about vulnerable Maryland with threats of sea level rise. Now, each time after we read this kind of articles, some questions may come to our mind. Questions such as, is this really happening, or is this just another political agenda? Or maybe a question like, if this indeed is happening, can we predict the impact of those effects before they occur? And the last question, maybe the most important one, is we ask, is there something we can do about it? Now, climate change, global warming, and sea level rise are most often discussed and debated topics nowadays. But in the meanwhile, many observations have shown that coastal inundation is becoming the most costly, most deadly, and most frequent coastal hazard that affect the coastal community. For example, in our Eastern Shore region, now it is ranked the third most vulnerable to coastal inundation in the whole United States, right after Louisiana and southern Florida. So now we know that the ocean provides fuels to the hurricanes and tropical storms. Now, warmer ocean will likely lead to more frequent and much stronger hurricane or tropical storms. So let's take a look at this picture here. This one shows the number of hurricanes and storms each year from 1944 to 2006. Now, if you look at this part of the picture, you can see the clear increase of the number of named storms in past 2 decades. Now, this is the observation data of mean sea level in Baltimore area from 1895 to 2014. Now, in fact, in the Chesapeake Bay region, the mean sea level rise is twice as high as the global mean. So many observations have shown as the world gets warmer as more water is added to the ocean, more severe inundation will occur. Now, during hurricane, now the wind will move around the hurricane eye on the surface of the ocean, and it will create a vertical circulation and also create an abnormal lift of the water above the ocean surface. Now, on the deep ocean side, this is not a big deal. The water will simply flow away without causing too much sea level rise. However, towards the inland, that is a big problem. As the water is being pushed towards the shallow bottom of the ocean, it has nowhere to go but go upwards and inland. Now, in reality, the storm surge only contributes partly to the water level rise during hurricanes. Now, the sea level rise we were talking about early on, the high tide that is caused by the pull between the moon and the earth, and this is extremely important in those semi-closed estuarine regions. The heavy rainfalls occurred before or during hurricane. The breaking waves that caused by the strong wind, all those factors combine together to cause coastal flooding. Now, observations of the past and the present play a very important role in the study of coastal inundation. However, as we all know, the observation of the future is not available at this moment. So, to be able to predict the future coastal inundation event and understand their impact, we need to rely on mathematical models. Now, the mathematical model that is used to study storm surge is based on this set of shallow water equations. Now, the reason we call it shallow water is because we are only considering the shallow continental shelf. Okay? So the two terms on the left, they represent the water velocity, change of water velocity with respect to time in both horizontal directions. And this next term here represents the water height and also the storm surge height, the change of that with respect of time. And all those changes on the left-hand side of the equation are determined by the terms on the right-hand side. So the first one is the gravity force. The second one here is the Coriolis force that's caused by the Earth's self-rotation. Since we are only considering the shallow continental shelf here, F is set to be constant here. And the last term here is the wind stress on the surface of the ocean. And now, it will take more than a few slides, but I'm going to fast forward. So this mathematical model can be transferred into a computer program and written in a programming language with a very nice name called Fortran. And this program is used to predict the future coastal inundation, the storm surge condition, at any particular location during the hurricanes. Now, there are two special features about this model that worth mentioning. The first feature is this model is coupled with an atmospheric model and a general circulation model. Now, the atmospheric model is used to simulate the atmospheric moment during the hurricane. So it will provide us with the wind stress that's needed in our shallow water equations. Now, the general circulation model is used to study the global circulation of the ocean. So it will provide us with a boundary condition for our coastal ocean model. Now, the next feature about this model is that it uses unstructured finite volume grid. And this grid provides us with a lot of flexibilities and improve the efficiency of our computer program. As you can see here, it allowed us to set different resolutions for different regions that we study. So for example, in the area that we are most interested in, like say Cambridge downtown, maybe Blackwater Refugee, we set a finer resolutions, say is 100 meters. And this will give us a better simulation of the indentation effect at the street level. And all the area that are less interest, for example, like on the surface of the ocean, we can set a coarser resolution, say 10 to 20 kilometers. And this will allow us to simulate a much larger region effectively. So when this model runs on a cluster of 500 nodes, it will take 3 to 4 hours to predict a forecast for 3 to 7 days. So to make our model more accessible by general public, we also develop a web-based visualization software. And this software will take the data produced by the mathematical model and combine that with the geographic information using this Google Earth or Leaflet library and display the result in a web browser. So any user who has access to a desktop computer, a tablet, or maybe even a smartphone can visualize our storm surge prediction produced by our mathematical model. So next, I'm going to show you some fun part. So 2 movies about our model prediction. The first movie is our model prediction for Hurricane Isabel for Dutchess County only. And the color indicates the water depth. You can see the flooding, the water coming into the bay and then gradually come out. And this is a recent simulation of our model for Hurricane Arthur, which happened this just past summer, July. And the left panel here shows the atmospheric model simulation. So in this movie, you can see the path of the hurricane eye traveling along the coast. And the right-hand side here is our model simulation. So again, the color indicates the water level, and the arrows indicate the wind direction and the strength of the wind. And you can see actually the water is being pushed out of the bay because of the wind direction. So that's why wind plays a very important role in the prediction. So now the scientific study have shown that enough convincing evidence that more severe coastal inundation will occur due to the climate change, the global warming, as well as the sea level rise. And our mathematical model, our computer program, and also modern computer technology allowed us to accurately predict the future coastal inundation and visualize their impact. Unfortunately, many cities in coastal cities in this country, they tend to ignore those risks. And some state governments actually are very reluctant to delegate authorities and allocate resources to deal with this issue. And there is a very interesting article I read 2 years ago. Like in North Carolina, the state legislature actually passed a bill. And this bill would only require the state agents to estimate the future sea level rise based solely on the linear projection of the historical data. They simply ignore the fact that many models And many field observations have shown that the rate of sea level rise can change and is changing over time. So now go back to the last question I asked early on. Can we do something to reduce the vulnerability and improve the resilience to this kind of coastal disaster? I think the answer lies in our policymakers, the state, local government, insurance agency, and most importantly, it's our general public. So are you guys ready? Finally, I would like to thank the collaborators from all three institutions. Thank you. Yes?
Okay, so you showed this fantastic visualization. So is this program set up to where the users can effectively look at whatever part of the world that they want to look at?
As of now, no. So what we did is, when we do the simulation, model simulation, we can simulate Middle Atlantic region and including Norfolk area. But when we do the visualization, combined with the geographic information, it is a very time-consuming process. Yeah.
So you have the simulation which is predicting what's going to happen. How close? I imagine, of course, you can now.
They did a pretty good job with. I was talking with Karen the other day. They did a pretty good job with the Arthur prediction. Actually, you know, if you watch the TV, they said, I think the TV said it will not land. But the model prediction, I say, it will touch the land. So, and then gradually, if you keep watching the news, the TV, they change their prediction as well. So the model is doing a good job in terms of prediction, yeah. Mike, you have a question?
Yeah, you had that one chart that talked about the number of named storms, I think since 1940
Uh-huh.
2006. With more data technology, do those criteria ever change a little bit? Or are they fairly constant? What
to name the storms? I think it is still the same. And also right now, there are more winter storms now. Usually the names are referring to the summers. And now we have some winter storms now as well, but they don't usually have a name for the winter storms. But the number of them are increasing, yeah. Yeah.
So how can you speed up the calculation? Because that seems to be something.
Yeah, maybe that's the next project we'll do with our GP. Yes, yeah, the calculation is an issue. And right now, we're using like a cluster of 500 nodes, so it is fast. However, the process of producing those visualization with the GIS information involved still takes time. And I think you have very good points. I think the next step maybe try to collaborate with some of the expertise in our department, you know, doing parallel computing with that aspect. I think that's definitely a way to go, yeah.
Great.
Thank you.